surface area of revolution. So let's say you are given a curve f of x, and we revolve this curve about the x-axis, and we want to calculate the surface area of this solid. Now think about this. Remember when we calculate the area, we calculate the measurement of the arc length. We looking at the we divide the curve into small segments, right? Now let's think about if we revolve each of this segment, this estimation about the x-axis, each of this part is a cone cut off the top, right? So ideally, that's what it is. So this is what we call. So this figure we call a frustum. A frustum. Okay. So let's see how do we calculate the surface area, the area of each of this band, and this band called frustum. Recall that, let's say we are given a circular cone, okay, and this cone have the radius R1, the bottom, the lateral, the height of the lateral is S, and the height of the cone is H. Then the surface area of this cone is given by this formula. Surface area of the cone is given by S equal pi r times small s. Or in this case, that is R1. Now, if we only want to calculate the surface area of the frustum, or this band, this figure over here. And so the cross section of the small cone and the larger cone, you can look at it as a similar triangle, right? So these are the similar triangle. Let me just draw that in for you. So you see this. So you have a large triangle making of the height of the cone, the base, this lateral side, and the smaller triangle is this one. Okay. Now we can set up this proportion such as R2 over R1, then have to equal S minus L divided by S. I'll go ahead and solve for S in this equation. S then equal R1L divided by R1 minus R2. For the length of then the lateral surface area of the frustum is S equal the area of the larger cone, lateral surface area of the larger cone, minus the surface area of the smaller cone. Okay. So this here we have pi R1 times S minus pi R2 times S minus L. I can factor this to get pi times L. I can simplify it in the way that we know that S is equal to R1L divided by R1 minus R2. Yeah, so I will substitute this into my formula. Pi R1 times R1L divided by R1 minus R2 minus pi R2 times R1L divided by R1 minus R2 minus L. We simplify this and clean it up. We get this equal to pi R1 plus R2 times L. So we will use this formula to calculate the surface area of each band formed by revolving the line segment about the x-axis. And let's just take a look at the representative of this band, the small band. And so let's say here you are given this curve. And here is our xi. This is xi minus 1. So then this is our f of xi minus 1. And this is where we have f of x of I. So this little band here that we're looking at, and we're revolving it about the x-axis. So this little band here. Okay, so then we can say that, okay, this distance, delta x equal x of I minus x of I minus 1. Delta y, the change in y, equal f of x sub I, right, minus f of x sub I minus 1. This means this formula S equal pi R1 plus R2 L can be rewritten as pi times f of x sub I minus 1 plus f of x sub I, and L is just square root the length of the segment, that is delta x squared plus delta y sub I squared. Okay. This meant that we are looking at the surface area. We will add all of each small area up equal the sum when I equal 1 to n of 2 pi times f of x sub I delta x 1 plus f prime of x sub I square. Okay. And let n go to let n approaches infinity. We now get in the formula for the surface area, that is 2 pi evaluate from a to b of f of x times square root of 1 plus f prime of x squared. The formulas doesn't change even if we then decide that we take in the integration with respect to y. Okay, so let's take a look at our example. Find the area for the surface generated by revolving the curve y equal 2 square root of x. For x is between 1 and 2 about the x-axis. We first will find the derivative of y. So y prime is equal to times 1/2 x to the negative a half. This clean up to be x to the negative a half. And then y prime square is equal to x to the negative 1. Let's plug this into our integral. So the surface area is equal to 2 pi times the integral evaluate from 1 to 2 of f of x times 1 minus y prime dx. So let's simplify this. So assign square root of 1 minus 1 over x is simplified to x plus 1 over x is simplified to square root of x plus 1 over x. So 2 square root x times square root of x plus 1 over x is simplified to 2 square root of x plus 1. Okay. So this meant our integral s equal 2 pi evaluate from 1 to 2 of 2 square root of x plus 1 dx. That is 4 pi from 1 to 2 the square root of x plus 1 dx. And we will do a u substitution. We have to change the upper and lower limit. So the surface area equals 4 pi evaluate from 2 to 3 of square root of u du, and this equal to 8 pi over 3 times 3 root 3 minus 2 root 2. Next, we have the surface area generated by revolving the curve x equal sine of y. For y is between 0 and pi. So first of all, we will calculate what is x prime. Well, x prime equal to cosine of y. This means x prime square equal cosine square of y. So the surface area equal 2 pi, the integral from 0 to pi of sine of y times square root of 1 plus cosine square of y dy. And we will estimate the value of this integral by using Google Sheet again. Okay, so let's pull up our Google Sheet. So here's my variable y. Here's g of y. And here's my integral. Now, when y is equal to 0, the value of this integral equals sine of 0 times square root of 1 plus cosine squared of 0. So at y equals 0, this integral is at 0 because sine of 0 equal to 0. So let's put in g of y. This is 2 pi times sine of y. Y is being defined as C3 times square root of 1 plus the cosine square. So power cosine of C3 square. Here we have 2 times pi, so the way we put pi is we say pi. It will come up with the function. Close. Okay. And then when you add in the pi into the next line, you do quart from 0 to pi. And we get these lateral, the surface area of this is 14.42.